Harmonic analysis of blood pressure waveforms is another important part of this lecture, because we should be aware about the characteristics, about the contents of the waveform in order to fabricate a good recording system. As you can see, the basic sine wave components of any complex time-varying periodic waveform can be dissected into an infinite sum of properly weighted sine and cosine functions of the proper frequency. You can see the original waveform of a sample blood pressure A, and as you can see, we can divide this waveform into its fundamental components of the same frequency as the blood pressure waveform and its significant harmonics. The first 6 harmonics, as you can see, from 1, 2, 3, 4, 5, and 6 harmonics, and also we can generate or reconstruct the synthesis of these first 6 harmonics together with in waveform B. As you can see, B is the synthesis of first 6 harmonics of A. As you can see, wave B are so similar to wave A. B is the estimation of A with only first 6 harmonics, and also we need only these coefficients, these percent of amplitude or coefficients of each harmonics is enough to generate B. Okay, compare the original waveform and the waveform reconstructed from the Fourier 6 first components or harmonics. As I mentioned in the previous slide, harmonic analysis is important to us. Also, in these kinds of analysis, measurement of system response is also important too. And harmonic analysis is related to the system response analysis also. The response characteristic of a catheter sensor can be determined by 2 methods. The first one is measuring the transient step response for the system. This method is the simplest and most straightforward technique. And the second one is measuring the frequency response of the system. This is this method is complex, and we use such a method to analyze the response exactly, or analyze the response in details. A potentially more accurate method, but a more complicated one, because it requires special equipment involves. The basic of first method, the transient response method, is to apply a sudden step into the pressure catheter and record the resultant damped oscillation of the system. This is also called the POP technique or pop technique. In this technique, we have a chamber here full of a liquid, a solid liquid, up to a level. We have an empty space here, full of air. Also, this space is covered by a flexible surgical glove. We have a hole at the bottom of this chamber where we insert the catheter via this hole inside the solid. Also, the catheter is connected to the sensor. The pressure, the air pressure in this region will controlled by a gauge and also a three-way stopcock and a sphygmomanometer blob to control, to increase or decrease the pressure inside this empty region. And we have a system, we will set the pressure inside this air to a situation, to a set point of pressure, and using a match we can suddenly brush this inflated glove, surgical glove, and after this situation, this suddenly explosion, we can measure the response of the sensor, as we will show in the next slide. As we shown in the previous slide, we set the pressure in the air above the solid to a specific pressure, input pressure, and after suddenly brush the inflated glove, the pressure inside that space will be suddenly reduced, and therefore the pressure applied on the sensor inside the solid will be reduced suddenly, and therefore we can now measure the sensor responses using our electronic amplification part. And as you can see here, as a general response, we have a second order response. And using the important points of this response, these peaks, the slope of damping, we can measure the important parameters of the second order response by these equations. And now we have the damping ratio, also the undamped natural frequency. Pressure sensor transient response using a negative input pressure is recording on the top channel, and also the bottom channel is sensor response for the Satam P23GB sensor connected to a 31 centimeter needle catheter. As I mentioned before, sinusoidal frequency response method is the second method for finding the frequency response characteristics and parameters of the sensor. But as I told you before, this method is complicated but accurate. As you can, sinusoidal frequency response method is more complex because it requires more specialized equipment. As you can see here, we have a chamber also here full of saline, and the catheter inserted from this hole to this chamber. A low frequency sine generator drives an underwater speaker. This is the low frequency sine generator, and this is the underwater speaker that is coupled to the catheter of the pressure sensor in this chamber. And also the sensor connected using this catheter. This low frequency sine generator will drive the underwater speaker to apply various exact frequency, and in this situation we can monitor, we can measure the accurate and exact response of the sensor for that specific frequency generated by the low frequency sine generator. But as you can see, an ideal pressure sensor with a frequency response from 0 to 100 Hz is connected directly to the test chamber housing and monitors input pressure, because we should be sure about the generated frequency. We should, first of all, we should sure about the generated sine wave by this low frequency generator, and after that we can compare the output of the sensor with the output of ideal sensor. As you can see, the system can find the response of the system in various frequency in the range of 0 to 100 Hz, and now we can plot a good chart for the response of the sensor. As you can read, we can find an accurate model for the catheter sensor system by determining the amplitude and phase of the output as a function of frequency without the constraint of the second order system model required in the transient response case. In some cases, resonance at more than one frequency may be presented. Therefore, we should be careful about this resonance. Maybe it leads to some damage. Next page are important for your exam. In these pages, we have some sentences which analyze the formulation, the methods, the frequency response, and the performance of the catheter. And also you should read it, you should analyze it, you should remember these sentences exactly. For example, as you can see here, the values of the damping ratio and natural frequency are functions of various system parameters, and these parameters are important for us and also important in your exam. Minute air bubbles, which increase the compliance of the catheter manometer system, drastically decrease the damped natural frequency. For example, for a PE 190 catheter of length 10 to 100 centimeters, the damped natural frequency decreased by approximately 50 to 60% for an unboiled water case compared to a boiled water case. And also, as you can see here, we can use boiled water instead of unboiled water to decrease the bad effects of bubbles in the saline water. Also, length of the catheter are inversely related to the damped natural frequency. For Teflon and polyethylene catheters, for the diameters tested in this range. The linear relationship between the damped natural frequency and seem to hold within experimental errors. A linear relationship between the inner diameter of the catheter and the damped natural frequency for both polyethylene and Teflon catheter as predicted by the model equation. In comparing the effect of catheter material on frequency response, because Teflon is slightly stiffer than polyethylene, it has a slightly higher frequency response at any given length. The increased compliance of silicone rubber tubing causes a marked decrease in frequency response. The authors concluded that silicone rubber is a poor material for determining parameters other than mean pressure. All these findings are based on the equations and experimental results. The damped natural frequency was linearly related to the needle bore for needles of the same length. I emphasize that all these sentences are based on equations. You can refer to the equations. We talk about RC, LC, CD, also the frequency, the undamped natural frequency, the damping ratio, and other equations in this lecture. The connector serves as a simple series hydraulic damper that decreases the frequency response. Remember, the fewest possible number of connectors, tightening fitting of the connectors, and a water seal are suggested to reduce the bad effect on frequency response also. Coils and bends in the catheter cause some change in the resonant frequency. However, the magnitude of these changes was insignificant compared with change caused by factors that affected compliance. Bandwidth requirements are a function of the investigation. For example, if the mean blood pressure is the only parameter of interest, it is of little value to try to achieve a wide bandwidth system. We don't want a wide bandwidth system for measuring only the mean pressure. It is generally accepted that harmonics of blood pressure waveform higher than the 10th may be ignored. The bandwidth requirements for a heart rate of 120 beats per minute or 2 Hz would be 20 Hz, for example. For a perfect reproduction of the original waveform, there should be non-distortion in the amplitude or phase characteristics. The wave shape can be preserved. However, even if the phase characteristics are not ideal, the waveform is delayed in time depending on the phase shift. measure of the derivative of pressure signal increase bandwidth requirement because the differentiation of the sinusoidal harmonic increases the amplitude of the component by a factor proportional to frequency. In this slide, we will talk about some typical pressure waveform distortions. And as you can see, the first waveform A, is the undistorted example, is an undistorted example of pressure waveform, recording of an undistorted left ventricle pressure waveform via a pressure sensor with bandwidth DC to 100 Hz. But the waveform B is a is an example for underdamped response where peak value is increased. As you can see, we have some overshoot from the real value. A time delay is also evident. In this recording, you can see a small time delay. The amplitude of the higher frequency components are amplified. That is a bad recording. Also, at the end of this falling edge, we have an undershoot. This is bad too. Waveform C is for overdamped response. Overdamped response that shows a significant time delay. As you can see, we have a significant time delay and an attenuated amplitude response. Higher frequency components are attenuated. This is because of some bubbles in the saline water. This slide is about those figures in detail, and I ask you to read it by yourself. In this slide, pressure distortion, bubble and heap are discussed. The undistorted pressure waveform is the waveform A, and air bubbling catheter is waveform B, and catheter heap distortion is the waveform C. The low frequency oscillation that appear in the blood pressure recording. This may occur when an aortic ventricular catheter in a region of high pulsatile flow is bent and heaped about by the accelerating blood. This type of distortion can be minimized by the use of stiff catheters or by careful placement of catheters in region of low flow velocity. It's important to exact and correct location. We should locate the sensor, the catheter, in a correct location. Location is one of the most important parameters in recording pressure inside our vessels and blood vessels and heart chambers. When